Yeah, perfect. Thanks a lot. And I'd like to talk a little bit about how we at ResearchGate got our pipeline for stats computation migrated from Storm to Flink. So this is mainly the basic and classic application for streaming. Counting things and counting things at scale might sound easier than it might be. So short introduction to myself. My name is Gunia. I'm working as an engineering manager for ResearchGate. And for all of you who don't know ResearchGate, let's start with a short introduction what ResearchGate is doing. So ResearchGate is the platform for scientists nowadays, where scientists share scientific research, they connect to other scientists, they share data, they share publications. So a lot of research is actually being put on the platform, is being consumed on the platform. And one of our major jobs and one of our mission statements is that by building products and building tools that help scientists, we are able to make science more efficient and make research open to all. So one of the products that I just mentioned is, of course, the stats product. And to better understand what this stats product actually does, let's take a look at an example and how it actually produces stats that are then reused in our system. So perfect example is the publication detail page. So what we see here is actually a screenshot from our platform. It's how we display publications to users. So it contains the most important parts for a publication. One is, of course, the title. Then we have a couple of authors. Then you get an abstract, maybe linked data, and if I would scroll down further, if this wasn't a screenshot, you would see the full text and could consume the full text directly on the platform. If we look to the upper part of that screenshot, we already see some stats popping up, right? So we see the number of reads, the number of citations, number of comments, number of recommendations, and those are already delivered by our stats product. So how do we actually compute stats and provide stats to our users? If a user looks at that platform or looks at that page, we will create a business event. And this business event will contain data that we then use in our stats pipeline. So as a starting point, look at this, create a business event that is then injected into our pipeline. After we process those business events, of course, something comes out. And one of the use cases for the stats that we produce and that we store in our systems is, of course, data that we provide to our users. Based on the publication read example that I just gave you, of course, the number of reads is interesting to our users. So this is, again, a screenshot from the platform. It's the stats overview widget. So you see that it already contains numbers of different granularity and of different breakdowns. So the upper number, the 44,000 reads, is the number of reads that the user got in all time on all the items, on all the research items that they actually uploaded to the platform. The graph in the center of the screenshot already provides a breakdown. It tells the user how many reads he or she got in the last weeks, in the last 8 weeks, whatsoever. So there's already a different granularity that we see here. And then if we look at the lower left corner of this, we see a further breakdown, broken down by what has actually been read. Because as I said, it's not only publications that are shared on the platform, it's also data sets, questions and answers, project update reads, and so on. So this is, again, another breakdown where our counters inform the user about what has been read where. But, of course, we're not using those counters only for our users. We are a massively data-driven platform. We want to understand how users will use the platform to make it better, to really find which features are used by users, which they like, which they don't like. So the next screenshot that I want to show you are the counters that we use ourselves. And obviously, they are not as beautiful as the ones that we show to our user, but they are also only used internally. But those counters already on those graphs are based on counters that provide additional breakdowns based on the business events that we have. For example, in the upper left corner, you see where the user did actually read their publication. Did he read it on the publication detail page that I just showed you? Did they download it, or did they read it completely different part of the platform? The upper left corner, the upper right corner tells us where if those publication reads are performed by logged in or logged out users. The upper lower left, for example, which type of publication got read how often. So after I showed you some use cases and how we actually use the data that our stats pipeline provides and creates, let's take a look at the requirements that we have. Of course, the most important requirement that we have is correctness. If our counters were incorrect, neither our users nor ourselves would have any benefit from that. So the first and most important requirement is correctness at that point. The second requirement is near real-timeness of counters. So if somebody reads my publication, I want to be informed about that, right? I want to see the counters increasing, and in an ideal world, as real-time as possible and not 1 day later. And the last part, the adjustability, which is our third requirement, is based on a specific use case and better understandable if I give you an example. One example is that, of course, we have crawlers on the platform. And not all crawlers are well-behaving crawlers, thus identifying themselves as crawlers. So really being able to adjust counters when a bad-behaving crawler issued a read on the platform is good for us and good for our users, because crawler reads are not reads that are of any interest to our users because it's not actually somebody consuming their research. So let's take a look at how we did it before we actually migrated over to Flink. So on the left side, we see a couple of producers, right? Those producers will produce the business events that I just told you about. And those business events back in the good old days have been injected into ActiveMQ. And then we had like a storm topology running that would have a spout. This spout would discover the queues, it would consume messages from the queues and then perform calculations. The outcome of that calculations would be increments on counters that we store in HBase. So counters processing of business event would cause increments directly on the database. So we had a counting platform, right? Why would we change it, right? Never change a running system, and whoever's sitting here probably has had issues with changing running systems in the first place. So let's take a look at the problems and the drawbacks that the original solution actually had. Let's start with the counting scheme. So what we did, we get a couple of events, those are flowing in time, and every event can increment one or more counters, right? Per every event we extract data and we'll increment one or more counters, and those will be simple +1 operations. That's the counting scheme that we had, and that's also the counting scheme that Storm as a stateless processing platform, stream processing platform, enabled us to do. What's the problem with that? So the first problem with that is that it's of course inefficient. Single increments are inefficient. We roughly have 1 billion increments per day based on the events that flow through our system. And the problem with that is if we perform those single increments, the load and the write load that we will put on our database will grow linearly with the number of publications or, of course, with the number of activity we have on the platform. And this is actually not what you want to have. You want to have a more efficient way of performing those increments or updating those counters. The second problem is based on the fact that we're performing increments in the beginning of that, right? The at least once semantics in combination with the single increments that we're performing will cause problems when messages have to be reprocessed. For example, something goes wrong, Storm will reprocess messages, thus this could cause counters to increment it twice, 3 times, whatever. So to enable us to really fulfill our most important requirement, which is correctness, we need to have additional tools, additional operations running to actually check and fix counters if this is necessary. And this is actually not what you want to have, because the operational difficulty increases by that solution. So let's take a look at the steps that we took from the originally stateless counting and stateless processing of our business events to finally stateful counting. First of all, let's take a look at the overall architecture that we have nowadays before diving into the more flinky parts of that. Again, we have the producers producing the business events. Nothing changed from that side. But nowadays, we're not ingesting them into AMQ, but we're writing them to Kafka. And where Storm was before, now there is a Flink streaming processor. And this Flink streaming processor uses a Kafka sink to which we output the messages or results that we then will perform database operations on. And then we have a message dispatcher which will read from Kafka and write to HBase via an intermediate service. This is actually a pattern that we use at ResearchGate, where we output results from streaming jobs and streaming applications to Kafka, for example, to get better control about the write load that we put on our database output systems. But as this is Flink forward, let's focus on the Flink part of this, right? So what do we want to achieve with that, right? What are the goals of our migration here? So the first one is, of course, we want to migrate Storm implementation to Flink. Basic reason for that being is a consolidation of our technology stack. So we've been a Flink company since years. We have a lot of Flink batch jobs. We have a lot of Flink streaming jobs. So we want to get rid of Storm because it's easier for new hires and for people switching teams to get into the technology if the technology stack is smaller. Second step is we want to improve efficiency and performance of the systems, thus get a better behavior of our database operations. And the third one is we want to improve the ease of operation that we have. So let's take a look at the baseline implementation. So the basic logic was to really take the processor and the topology that we had in Storm, have it migrated over to a Flink processor and see what comes out of that. And basically does the following steps. It reads inputs from Kafka. It performs a flat map operation because one business event can increment a couple of counters in that case. Those results will be output to Kafka and then written to a database, right? Nothing spectacular here. But by simply doing this, we already got the nice result that we reduced the lines of code by roughly 70%. And this is simply because of the fact that Flink comes with high-level APIs that make our life easier and make the implementation that much easier that the number of lines of code that we actually needed to get to the exact same behavior was significantly reduced. And less lines of code, less bugs, better maintainability. So this was already a nice result that we get by simply moving the same logic over. So let's take a look at our what to achieve list. We made it, we migrated Storm over to Flink. So let's take a look at the second challenge. Like, how could we improve the efficiency and performance of our overall implementation? So you remember that the basic problem is that we're performing +1 operations on every event. So if it was possible to do a pre-aggregation, thus not performing 10 times a +1, but to perform a +10 instead, and thus reducing the write load, that would be pretty cool. So Flink enables us, of course, and the typical operator that you want to have for that is, of course, a window. So what we did is we added those lines of code here. We keyed the stream based on an entity key that's coming from the keys from the flat map operator, and we use a simple time window to pre-aggregate those results. Right? And instead of outputting the results from the flat map operator directly, we then output the pre-aggregated results to the Kafka sink. Again, our dispatcher will write to HBase via the intermediate service, and the data ends up in HBase. So here's the code for that. And you saw that the operations are pretty simple, and the code is also pretty simple, which is a really nice thing, because this is what you want to have. Again, there's a flat map, there's a key by operator, and down there is a time window that will pre-aggregate the increments that we form on the database and then fold them, and then they're going to end up in a Kafka sink, which I didn't print on this one. So let's take a look at the counting scheme and how it changed. Right? So that was the original one that we did in Storm, that we also did in our baseline implementation in Flink. Now we added this window to pre-aggregate our increments. So the counting scheme changed. Right? Instead of doing those +1, we now wait for the window size and do a +2 and a +2 down there. One thing that becomes obvious if you look at that is that you trade real-timeness for pre-aggregation. Right? The bigger the window, the bigger the gains of the pre-aggregation will be, but the lower the real-timeness is. But it gives you a nice control over real-time versus write loads, and this is actually a pretty cool feature that enables you to really fine-grained control how much write load versus how much real-timeness you want to have. Let's take a look at the benefits again. Obviously, it's easy to implement. You saw the lines of code. There's some operators in between, some logic, but it's really easy to do this. It has a pretty small resource footprint. We were able to run this with 2 yarn containers with roughly 4 gigs of memory at that point, because the windows were pretty small. And the third one, it's actually pretty amazing, but that, of course, depends on your counting scheme and how good the pre-aggregation works at that point. So what we did, we had those roughly 1 billion increments per day by simply pre-aggregating them by such a simple window operation, we were able to reduce them down to 200 million increments, thus roughly 80% of the write load. And you can believe me, your database team will love you for doing something like that, because nobody ever does that. So pretty good, pretty easy, and nice benefits from that. So again, what do we want to achieve? We obviously migrated. We improved efficiency and performance. And the third thing is the challenge that I wanted to look now. So let's take a look at the counting scheme again. So this is nice because it reduces the load, it does a pre-aggregation. But the problem is still the same, right? We do in increments. And increments are the problem that occurs if you, for example, have to restart your processor from an earlier save point. It will reprocess the same messages, it will output results, and if those results are increments, you will increment the same counters twice. You will be more efficient because you increment less, but the results would still be wrong. So what you actually want to have at that point is idempotent counting. So you don't want to perform increments, but what you want to do is you want to perform put operations. So the state of the data should not be retrieved via increments, but the state of the data should be part of the processor state. And if you're able to do this, for example, in that case, the value of this counter is 40. And now we get an increment plus 1, and the value is 41. And the output is not going to be the increment operation. The output is going to be the current state of the counter. In that case, you can go back and forth in time, reprocess messages, update your state internally, and then output the data and the state of that processor to your Kafka sink, and have the data always correct in HBase. Right? So let's look at that on a schema level for the overall processor. So I used the colors that also correlate with the code that you will see to make it easier. So again, we have a stream coming in, right? We key by minute, because the smallest granularity that we have is a minute counter. That will then end up in a higher granularity counter, which I'm going to talk about later. So we have the window that's doing the pre-aggregation. That's the one that's saving efficiency and reducing the number of increments we have to perform. The output of that window will then be written to another stream and keyed on a day granularity, because this is the next higher granularity that we have. So the window that we added at that point is the solution for this idempotent counting problem. So what we want to do is actually have the data for this day stored in a Flink, in the Flink state, and then being outputted. Thus, the second window accumulates the states for counter with day granularity. Thus, this window will, of course, be way bigger. Right? Let's take a look at code. Again, the code is simple, which is really nice. So what we have here, the left part is again the one that we saw before, right? That's the pre-aggregation part. The red part is the new one. So we again key based on a day granularity key, and then have a time window that's way bigger than the first one. And this first one, this window has a custom trigger, because what we want to have is, of course, the near real-timeness, right? And if we would output after the window fires, so after the 1.5 day window size, users would have to wait again for their counters to pop up, which is not what they want to have, which is like we use a custom trigger that will simply fire on every element. Right? This enables us to always output the state of the counter when something new comes in, thus to update the state of the numbers for our users in near real time, but still contain the state in the Flink streaming processor. So let's take a look at the graphs again, right? So the problem that we solved is this one. That was the problem of counters that are based on closed window and closed window counting, right? This is the number for the week ending July 16. So to get the number of reads per week, you fetch the seven counters for the days and sum them up, right? What's still open and what's a little bit more problematic is this guy. So this is an all-time counter. It contains the data for all time, for all reads that have ever been taken place on this thing. So the difference with that one, the day granularity is finite and can be closed at some point in time, right? A day counter will not be updated after the fact. You might have some late arrivals, but at some point in time, you will be able to close this window and output the day counter. By changing the platform over to our idempotent counting, we've been able to update those in an idempotent way and thus solve the issues of operational complexity and increase correctness and thus trust. The remaining problem that we have is the one that deals with how we handle those updates of counters that actually never closed. Right? This thing will stay open forever because as long as the platform is there, those counters might be incremented. So the first idea, of course, because this day counter update worked that well, why not use a window of infinite size? Right? So same logic, we key this stream, we update the counter and the internal state based on what's coming into this infinite state window and then output the result. So this thing has a couple of problems. Actually, creating the initial state is not trivial. So ResearchGate has been there for a couple of years, and our H-based cluster contains billions of rows. And really getting those data into an initial state in Flink is actually not a trivial problem. So we would have to be able to do this. Of course, it's doable. So there's nothing that's not doable. The second part is even more problematic. As said, this is like an open window counting problem. So the key space will grow infinitely, which means that also the state will grow infinitely. And this is something, if I don't have to do this, I would prefer not to. Right? Because I have heard some talks over here at Flink Forward where people say that managing huge state is possible, but it gives you complexity that if you don't have to take it, you might not want to. So this is why we came up with something else. So the basic idea being at that point, and the basic target that we want to tackle and the basic problem that we want to tackle is how we can update those all-time counters also in an idempotent way. So the basic idea is we should remember what we've done before, we should revert the previous operation and then apply the new operation. This is all based on the idea that we've been able, by our initial solution, to update the day counters in an idempotent fashion. So let's take a look at an example. So this is what we have. Let's say we have an all-time counter of 245, right? And the last update operation that we did was for the current day 5. So that means that we already updated this one all-time counter by the value of 5 today. So now, let's say we get a new incoming update for the current day. So 2 other people read my publication. The reads for that particular day will increase to 7. So how do I update this all-time number? So simple math. I revert the previous operation, so 245 minus 5, 240, and I apply the new value for that particular day. And then we put the row back into the database, which gives us the all-time of 247 with the current day of 7. Of course, this thing is not as easy as it looks like. You have to take care that, of course, you don't have any updates coming in from the site that will override that. So we will use mechanisms like optimistic locking on HBase to be sure that you're not overriding like on a stale row, for example. But in general, that's the schema. And now that brings me back to the architecture slide. So one of the reasons why we use this dispatcher scheme is to have better control over the write load that we put on the database system by having Kafka as an intermediate buffer in that pipeline. The other one is that we want to perform operations like the one I've just talked about, not in Flink directly. Which is why we have this service sitting here that's then going to fetch the data from HBase, update and perform those operations that I just talked about, and write it back using optimistic locking at that point. So let's take a look at the achievements and what we wanted to have. So we made it, we migrated Storm to Flink. We also increased the efficiency and performance of our overall platform by using a pre-aggregation window. And then we found a way to not only update day counters in an idempotent way, but also this open window all-time counters in a way that we can perform updates on a counter that's a moving target, actually. So the last part and the last steps of my presentations, I'd like to talk a little bit about the integration of stream and batch processing. Because one of the reasons why we wanted to move over to Flink is, as I said, we have lots of data set jobs, lots of data stream jobs running, and being able to benefit from the ability of reusing business logic, for example, is a nice thing that Flink gives us, right? So let's look at our use case again. So there are actually a couple of things that might be unknown at processing time. That's, for example, the bad behaving crawler example that I gave you guys, right? You might not identify the crawler directly. Your systems, your suspicious traffic detection might tell you a little bit later, but then you should be able to fix those crawlers retrospectively. Of course, there might also be things that change after the fact, which is the classic business requirements, right? You might require the graphs that I showed you, where we have breakdowns for publication type, for context, for logged in, logged out. But what happens if your product manager comes by and says, I want to have another breakdown where it's broken down by referrers, for example, right? So what you want to have is to be able to really reuse as much logic as you have to also solve these problems. So again, the nice part of Flink is that it comes with those data set APIs and the data stream APIs, and that it's really easy for us to reuse parts of the implemented business logic coming from the stream processing application and take it over to the data set application, so we can reuse the code that we've already written to process our counters. So by simply moving this over to Flink instead of having Storm in the first place, we've been able to reuse massive amounts of the code that we've written and additional building blocks that we have in the architecture overall. Yes, that's it. Thanks a lot, and I'm happy to answer your questions. Any questions? Even better. I'll be around if questions pop up, please.
I think the pictures icon you had going into Kafka, then going to Flink and writing back to Kafka again before you. Yeah.
That one?
Yeah. So why are you, and the dispatcher, can you explain that part, the Kafka sync? The Kafka sync, can you explain the Kafka sync as to what it's doing?
What the dispatcher of the Kafka sync is doing?
Yeah.
Ah, all right. So what this basically is, so at ResearchGate we developed building blocks that we can reuse to develop new applications. And the basic idea is, for example, that not every microservice that we spin up should deal with Kafka consumer logic. So what we did, we created a building block service that will consume and deal with the offset committing, partition assignment, all that stuff that you need to do if you want to do it on scale. And that's simply going to read data and use the REST APIs that our microservices are using. So those things will provide you with REST APIs and simply take a message and forward it, so that we don't have to have this consumer logic in the microservice that will have REST APIs anyways. All right. Yeah, thanks a lot.